This video is a step-by-step solution for the example entitled Heating Water at Constant Volume. In this example, you will learn about heating a given mass of water at constant volume and evaluating how the mixture of liquid and vapor evolves until all the water is in vapor form. Let's look at the problem statement as given to us. A closed, rigid container of volume 0.5 cubic meter is placed on a hot plate. Initially, the container holds a two-phase mixture of saturated liquid water and saturated water vapor at P1 is equal to 1 bar and a quality of 0.5. After heating, the pressure in the container is P2 is equal to 1.5 bar. Indicate the initial and final state on a TV diagram and determine the temperature in degrees C at state 1 and 2, the mass of vapor present at state 1 and 2 in kilogram, and C, if heating continues, determine the pressure in bar when the container holds only saturated vapor. First, let's do a critical read of the problem statement, highlighting in red the important information given and in green the information requested. Highlighted in red, we have a closed, rigid container of volume 0.5 cubic meter is placed on a hot plate. Initially, the container holds a two-phase mixture of saturated liquid water and saturated water vapor at P1 equal to 1 bar and a quality of 0.5. After heating, the pressure in the container is P2 is equal to 1.5 bar. Highlighted in green, we have indicate the initial and final states on a TV diagram and determine the following. A, the temperature in degrees C at states 1 and 2, the mass of vapor present at state 1 and 2 in kilogram, and C, if the heating continues, determine the pressure in bar when the container holds only saturated vapor. Let's start to develop the solution. The first thing to do in any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in a critical read of the problem statement presented here in a compact bulleted list form. A two-phase liquid-vapor mixture of water in a closed, rigid container is heated on a hot plate. The initial pressure and quality and the final pressure are known. The next thing we need to do is to summarize what we have to find. This is again the same information we highlighted in green in a critical read of the problem statement, presented again as a bulleted list. Indicate the initial and final states on the TV diagram and determine at each state the temperature and the mass of water vapor present. Also, if heating continues, determine the pressure in the container when the container only holds saturated vapor. The next step in the solution is to develop a relevant schematic. In this case, it was provided to us. However, let's highlight a few important pieces of information that were provided, which will help us develop our solution. The first thing to notice is that there is no mass entering or leaving the piston cylinder. This immediately suggests that a closed system approach is the correct one. Having recognized this important fact, let's select a system boundary. In our case, it is selected to enclose the content of the cylinder and follow the physical boundary of the piston cylinder assembly as delineated on the schematic with the red dashed line. The information provided is on the schematic, namely the initial pressure, liquid vapor quality, and volume are given, the pressure at state 2, and the quality at state 3, namely X3 is equal to 1 for saturated vapor. The next step is to develop an appropriate thermodynamic diagram to represent the processes, in this case the PV diagram as shown here. State 1, with the given initial pressure and a given quality of 0.5 inside the vapor dome. State 2 with the given pressure P2. And state 3 located on the vapor dome on the right side, indicative of a saturated vapor in that state. Note that the processes from 1 to 2 and 2 to 3 occur at constant volume, that is, along a vertical line on the PV diagram. The next step is to develop an engineering model, which is a set of simplifying assumptions which will allow us to perform the analysis of the problem. The water in the container is a closed system. States 1 and 2 and 3 are equilibrium states. And the volume of the container remains constant because it is rigid. Having completed all the required preliminary steps for our solution, let's develop the analysis. Two independent properties are required to fix states 1 and 2. At the initial state, the pressure and quality are known. As these are independent properties, the state is fixed. State 1 is shown on the TV diagram in a two-phase region. The specific volume at state 1 is found by using the given quality and the equation for the specific volume as a weighted average between the vapor and liquid values, which can be expressed as follows. V1 is equal to Vf1 plus x times Vg1 minus Vf1. From the pressure table of properties of saturated water at P1 equal 1 bar, Vf1 is equal to 1.0432 10 to the minus 3 cubic meters per kilogram, and Vg1 is equal to 1.694 cubic meters per kilogram. Substituting those numerical values in the equation above for V1 yields the following, which is equal to V1 is equal to 0.8475 cubic meters per kilogram. At state 2, the pressure is known. The other property required to fix the state is the specific volume V2. Since volume and mass are each constant in this system, the specific volumes are also constant. V2 is equal to V1 is equal to 0.8475 cubic meters per kilogram. For P2 equal to 1.5 bar, the pressure table of properties of saturated water gives us Vf2 is equal to 1.0582 10 to the minus 3 cubic meters per kilogram, and Vg2 is equal to 1.59 cubic meter per kilogram. Since V2 is clearly between the liquid and vapor values, state 2 must be in the two-phase region as well, as was shown earlier on the TV diagram. For part A, since states 1 and 2 are in the two-phase liquid-vapor region, the temperatures correspond to the saturation temperatures at the given pressures. The pressure table of properties of saturated water gives us T1 is equal to 99.63 degrees C and T2 is equal to 111.4 degrees C. Those are the first answers we were seeking, namely the temperatures at state 1 and 2. For part B, to find the mass of water vapor present, we first use the volume and the specific volume to find the total mass M. M is equal to capital V divided by small v. Numerically evaluating this expression gives us M is equal to 0.59 kilogram. Then, with the equation which defines the quality of a two-phase liquid-vapor mixture and the given value of the quality, the mass of vapor at state 1 is Mg1 is equal to x1 times M, or 0.295 kilogram. This is the first answer we were seeking for part B, namely the mass of vapor at state 1. Similarly, the mass of vapor at state 2 is found using the quality x2. To determine x2, we can use the equation for the specific volume as a weighted average between vapor and liquid values and solve for the quality. x2 is equal to V minus Vf2 divided by Vg2 minus Vf2. inserting the specific volume data from the pressure table of properties of saturated water at a pressure of 1.5 bar, along with a known value of V, yields the following. X2 is equal to 0.731. Then with the equation for the definition of quality, we can obtain the following. Mg2 is equal to 0.731 times 0.59 kilogram, giving us a value of 0.431 kilogram. This is the second answer we were seeking for part B, namely the mass of vapor at state 2. For part C, if heating is continued until reaching a saturated vapor state, or X3 is equal to 1, state 3 will be at the intersection of the saturated vapor line and a vertical line representing a constant specific volume, V3 equal to V2 is equal to V1, as was shown in the TV diagram. Hence, the pressure will be the corresponding saturation pressure. By interpolating in the pressure table of properties of saturated water, for Vg is equal to 0.8475 cubic meters per kilogram, we get P3 is equal to 2.11 bar, which is the answer we were seeking for the final pressure P3. To finish, I would like to make a few remarks. The procedure for fixing state 2 is the same as was illustrated in discussion of the TV diagram for water, used to locate the states in the table. Specifically in this example, since the process occurs at constant specific volume, the states lie along a vertical line in the TV diagram. In closing, in this example, we have learned about heating a given mass of water at constant volume and evaluating how the mixture of liquid and vapor evolves until all the water is in vapor form. We have also learned how to evaluate the final pressure reached when all the water is in vapor form. This concludes the step-by-step solution of the example entitled Heating Water at Constant Volume.